Let's see if we're getting any better with these PES photoelectron spectroscopy plots. When you're reading these along the x-axis going left to right, you'll just have to get used to this. This is decreasing binding energy. It's kind of unusual, but that's the convention, decreasing as you go to the right. And then on the y-axis is your relative number of electrons. And oftentimes you'll see this be the case where one of the peaks is 3 times the size of the others, and they're also very close to each other, and that's very characteristic of your s orbitals and your p orbitals at the same energy level. Right? P orbitals can hold 6 electrons and s orbitals can hold 2. So 6 is 3 times as big as 2. We know that's what's going on here, but let me show you an energy diagram of this. Is going to be argon. Argon has 18 electrons, 18 protons, 18 electrons, and so we'll fill them up using alpha-bal. There's your 1s. You got 2 electrons in the 2s. Follow Hund's rule. Yeah, 10 now, and then the valence electrons for argon are going to be in the third. This is not drawn to scale. It's going to have 8 electrons, and it's n equals 3. All right, I just violated Hund's rule. I know. Oh, let me do that again. There we go. So got 18 electrons there plotted on this energy diagram, not drawn to scale. And so in photoelectron spectroscopy, we're going to shine some, let me just do red here. Now oftentimes we'll use x-rays, but just use different colors here. So some amount of energy is going to get these valence electrons, the one in the farthest energy level in the p orbitals in this case. These electrons are going to start ejecting first, and they're going to be ejected with some amount of kinetic energy. We can measure all that. We know how much energy is going in, and so that's going to give you this peak here. Right? That represents the 6 electrons in the 3 p orbitals. All right, and that's going to require the least amount of energy. So that's why we're on this side of the graph. Notice it's a little bit more than 1 megajoule per mole, because there's the 1. You would expect the next one not too much farther after. If we give it a little more energy, these electrons are going to get ejected next. And so that's what you see. You see a peak that's a third of the size, and right here that's your 3s. The 2 electrons in the 3s orbital, so those are going to be ejected, and then nothing happens for a while, because now you're in the core electrons. And so if you do get enough energy there, eventually those electrons in the 2p orbitals, there's 6 of them, so it should match up with the 6, and the height should match up, right, with all the p orbitals, unless it's not a full orbital. But this is your 2p. Those are your 6 electrons in your 2p orbitals, and then not long after that, then you have the 2 electrons in your 2s orbital right there coming off, and then finally you have your, what is that, 1,000 times more energy. So this graph is not drawn to scale, because 1 to 10 is like that distance, and then like what's going on there, right? A lot of times they'll put like a little disc. Anyway, these are your 2 electrons in the 1s orbitals. So this requires the most energy, and we can do that because X-rays have a ton of energy, enough to get these electrons ejected. So there it is. So when you read these, oftentimes you're just focusing on the valence electrons to identify what element it is. So again, this is argon.